8.2 Cartesian equation of a line. So as a recall, y equals mx plus b is the equation of a line in slope y-intercept form. And we can rearrange this so that there's nothing on one side and everything else is on the other side. And this is standard form, ax plus by plus c. And this is the equation of the line in standard form, also called the Cartesian equation of a line. This is actually the one that we're going to be focusing on right now. So the relationship between slope and the direction vector. The slope of a line represented by rise over run, okay, y2 minus y1, so the difference in the y's over the difference in the x's. And the direction vector of a line is represented by vector m, a comma b. Okay, if the direction vector of a line, vector m, corresponds, if the direction vector of a line is vector m, this corresponds with the slope m equals b over a, and we kind of touched on that in the last section 8.1. Okay, except for when a is 0, because that'd be like a vertical line, and remember, when a equals 0, the slope is undefined. So if we take a look at this drawing right here, this diagram, if we have AB, we can say the slope is like rise over run. So B units up and then A units to the right, rise over run. However, when we take a look at direction vectors, all we do is we take this basically direction vector, we refocus it at the origin, which is 0, 0, and now it's a vector a comma b. Of course, the x component first now and the y component later, right? Whereas the slope is vector y, the change in y over the change in x. So it'd be the y on top and the x on the bottom. Okay, example 1. Determine the equivalent vector and parametric equations of this line right here. Okay, so when we think of the vector equation, we need a point first. So we already have a point, the point 2. We know that this is the y-intercept. So the y-intercept is 0, 2. So let's plug that in for the actual line, and we can actually start plugging that in for the parametric equations as well. Now, our slope is 3 over 4. So that makes our direction vector, so this is b over a, right? A comma b, we have 4, 3. So that's it. We put in a parameter, and we put in 4, 3. Okay, so we can write 4t and then 3t. So here is our vector equation of this line with a point and the slope converted into vector form. And here are the parametric equations of this line. Okay, example 2. For the line with this equation, determine the equivalent slope y-intercept form. So the slope y-intercept form, y equals mx plus b. Okay, we know that this is one of the points, and this we can convert into the slope. So this is a comma b. Our slope we know is going to be b over a, so our slope is -4 over -1. Okay, I'm going to write it as 4 over 1, or actually just 4. So we have the slope, which is 4, but we don't actually have the y-intercept, the b. So let's go ahead and plug in the point 3, comma -6. And let's solve for b. Okay, you can just rearrange. Yeah, I get -18 equals b. So therefore, our equation is y equals 4x minus 18. So we are able to go from vector equation to slope y-intercept form. Okay, so let's just recall. The slope of a horizontal line is m equals 0. Okay, and that means that it's m equals 0 over some number. Okay, which means that the direction vector is going to be, because it's b over a, it's going to be that number, whatever a is, comma 0. Okay, and the slope for vertical line is undefined. Okay, undefined means that it was some number over 0, which means that the direction vector is 0, comma b, whatever that number was. Okay, so let's determine the Cartesian form of a line with this equation right here. Okay, so we have a point on the line and we have a direction vector or the slope. Okay, 0, comma 2, which is a, comma b. We know that our slope is going to be b over a. So our slope is going to be 2 over 0. The slope is undefined, so is vertical line. Okay, this is a vertical line that passes through the point 1, comma 4. Okay, so it's going to look like this. That means that the equation is, and remember, vertical lines take on the form x equals, and then whatever the x-intercept is. So this one's going to be x equals 1. Okay, bring this over. We have x minus 1 equals 0, and that is the Cartesian form of this line. So the AB in the Cartesian equation, ax plus by plus c, so this right here, the a and the b, is actually a normal to the line, and it's named vector n. Okay, vector n equals, and then capital A, comma, capital B. That's how we denote that. So in this diagram over here, the blue line is the normal. Okay, and it's perpendicular to the red line. And it goes through the origin. Okay, so the line that we'd be talking about in this equation would be the red line, and then the blue line is normal to that. Because it goes to the origin, it lies on what's called the normal axis. If a line is drawn perpendicular to the red line, but does not go through the origin, then it's simply called a normal to the line. Okay, so example 4, determine the Cartesian equation of the line passing through this point, A, 4, comma, negative 2, which has this normal, 5, comma, 3. Okay, so there's two methods of doing this. First, we can use the dot product. Since we know that any normal dot the direction vector of our line equals 0 because they're perpendicular, of course. Okay, we can use that. So all we know is one point on the line. So say we know, actually, I don't even want that. Say we have A, and we have some other point, I don't know, let's call it X and Y. Okay, and then our normal is going to have direction vector 5, 3. Okay, so first let's find the direction vector of A, and then that point, let's call it P, point P. So AP is simply just going to be X minus, and then A is 4, comma, Y minus negative 2, so Y plus 2. That's going to be our direction vector, AP. Now, if we took that direction vector and we dotted it with the normal 5, comma 3, we should equal, like this should equal 0 because they're perpendicular. So let's go ahead and dot them. So we have 5 times x minus 4 plus, and then we have 3 times y plus 2 equals 0. So we have 5x minus 20 plus 3y plus 6 equals 0. So I get 5x plus 3y, and then just collect like terms, negative 20 plus 6, I get negative 14 equals 0. And that should be the Cartesian equation of a line that passes through 4, comma, and has a normal 5, comma 3. Also, I'm going to point out that these two numbers will always be the normal. The normal is going to be a comma b, and that's what they are actually talking about, because we know that this is in the form ax plus by plus c equals 0. Okay, let's look at another way of doing this one. Okay, we're going to do the same question, but method 2, we're actually just going to use straight like the Cartesian equation. So if we think about ax plus by plus c equals 0, we know that 5 comma 3 is going to be the a and the b. So already we know that it's going to be 5x plus 3y plus c equals 0. So what I'm going to do in order to find c is I'm going to sub in x and y into this equation. So let's go ahead and sub in 4 comma negative 2. Okay, so I get 20 minus 6 plus c equals 0. So 20 minus 6, I get 14 plus c equals 0. Bring that over. C equals negative 14. So we can go ahead and plug in this negative 14 back into the c, and we get 5x plus 3y minus 14 equals 0. That is the Cartesian equation of the line that passes through 4 comma negative 2 and has this normal. So let's just talk about normals of parallel lines. Okay, so since the slopes of parallel lines are the same, their normals will be scalar multiples of one another. In other words, basically like their normals are going to have the same slope as well. Okay, so how we denote this is like the normal number 1, the vector of normal number 1 equals k is some scalar multiple of vector normal number 2. Okay, and that scalar multiple is a real number and doesn't equal 0. So it just can't equal 0. Okay, and now let's take a look at perpendicular normals. Okay, so normals of perpendicular lines. So two lines are perpendicular if their dot product equals 0. Okay, so also if they're normal, if the dot product of their normals equals 0. So the dot product of the direction vectors is also 0. Okay, so if we take one direction vector and we dot it with the other, it's going to equal 0. Example 5. Show that the lines L1 and L2 are parallel and non-coincident. Okay, so when we're trying to prove that two lines are parallel and they're both in a Cartesian equation, what we want to do is first we want to focus on their normals. Okay, so if these lines are parallel, then their normals are going to be also parallel. Okay, they're going to be multiples of one another. So n1 is 3 comma negative 4, and n2 is 6 comma negative 8. So looking at these, we can tell that n1 equals 1/2 of n2. So yes, n1 is a scalar multiple of n2. So these two lines are at least parallel. Okay, so when we say non-coincident, we mean that they are distinct. Okay, they do not lie on top of one another. So let's just put distinct. So what we want to do now is we want to compare the c values. Okay, so we want to compare the number negative 6 with negative 12. Okay, is negative 6 1/2 of negative 12? Well, yes, it is. I think this is what mixed me up, because I know they're not supposed to be coincident. This is positive 12. Okay, so does negative 6 equal 1/2 of positive 12? No, there's no number that's gonna make line 1 some duplicate of line 2. So therefore, they're parallel and non-coincident. Now, 5b. For what value of k are these lines, line 3 and line 4, perpendicular? Okay, so these are both in Cartesian form. So let's go ahead and take the normals. So normal 3 is k comma 4, and normal 4 is 3 comma negative 2. What do we know about perpendicular lines? Well, their normals are also perpendicular, so therefore their normals, if we take the dot product, they will equal 0. So let's go ahead and take the dot product of these. Okay, multiply the x's, so 3k, and then add the y's, 4 times negative 2, so negative 8. And that, I guess we don't need a bracket, this is going to equal 0. So let's just go ahead and solve for k. So we have 3k equals 8, divide both sides by 3, I get k equals 8 over 3. Okay, therefore, k equals 8 over 3. We can also say that normal 3 is going to now equal 8 over 3 comma 4. Okay, last little topic, the angle between two lines. So the angle between two lines is defined by the angle between their direction vectors, A and B, where theta equals cos inverse A dot B on the top, and then the magnitude of A times the magnitude of B on the bottom. Okay, so example 6. Determine the acute angle formed at the point of intersection created by the following lines. Okay, so we have line 1 and line 2. We're going to focus on the direction vectors here. Okay, so negative 1 comma 3 and 3 comma 4. So let's write out the equation. Theta equals cos inverse. So now let's dot A dot B on the top. Okay, negative 1 times 3 is negative 3 plus 3 times 4 is 12. And that's going to be the numerator. Now our denominator is going to be the magnitude of A, which is just negative 1 squared plus 3 squared. Okay, times the magnitude of B, which is going to be 3 squared plus 4 squared. Okay, and now we simply calculate. So I get negative 9 on the top, then 1 squared plus 3 squared, which is 1 plus 9, I get root 10, times 9 plus 16, I get root 25. Okay, so cos inverse of negative 9 over, okay, so that gives us negative 9 over 5 root 10. And if we just put that into our calculator, we're going to get the cos inverse of a very small number, negative 0.5692. Okay, and now we get theta equals, I get in my calculator 124.69. If you think of this angle, I think of it as right here. Okay, that means that we just have to subtract it from 180. So 180 minus 124.69, and we will get our angle of 55.3 degrees.